So today's gonna be an interesting topic today. We don't have much time for it, but it's one of my favorites, and I will try to cover it thoroughly. This is gonna be called transformations. In particular, is transformation of functions. So, transformations of functions. Now, when we're dealing with functions, we're always referring to the most basic type of functions without any transformation as parent graphs. So parent graphs or parent functions, either or, are functions without any transformations. So if you recalled in, I believe, 2.2, we listed several parent functions. We had the constant function, we had the linear function, we had the quadratic, the cubic, all of the power functions. We also had the reciprocal function. We talked about the step, or the greatest step, or the greatest integer function, I apologize. The absolute function, and then I also hinted, I didn't put it in the list, but I also hinted about the square root function. That will play a role as well. I also gave it as an exercise for students to do to find the key features of those functions. Now, using those parents function, let's take example. We're going to take x squared. I like f of x equals x squared. This is a parent function. Parent graph. F of x squared. And this is going to have a relative shape of boom, boom, boom. Make this gray. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It'll have a relative shape located at 1, 1, 2, 4, 1, 1, 2, 4. And I do these points because sometimes I struggle in drawing the parent graphs themselves unless I draw key points. Something along these lines. All right, it's a parabola. So this is your parent graph, f of x equals x squared. Now, you have several transformations that can happen. In particular, you have transformations that include shifting, which means moving, / translating. And when you shift / move, you can only move up, down, oops, take that off. You can move in the directions up, down, left, and right. So you cannot move diagonally. If we're having any diagonal movement, we're going to have a combination of your horizontal and your vertical transformation shiftings. You have shifting, you have stretches / compressions. Stretches / compressions of a graph. You also have reflections across x and y axis. I apologize. You have stretches and compressions vertically, and horizontally. Stretches in these manners, vertically and horizontal stretches and compressions. You have reflection across x and y axis. So all of these set transformations that we need to really deal with any sort of parent graph. Any. And now, it's actually probably best for us to just look at a perfect example of this, and then I'll draw some examples later. So I'm going to be using Desmos in particular, and we have the function y equals x squared. So we have this parabola shape. Now, I can have all sorts of transformation. If I wanted to shift my function, let's say 2 to the right, it might look something like this. Boom. It might move 2 to the right. If I wanted to move my function, let's say upwards, 2 upwards, I might have something like x squared plus 2. Boom. I'm shifting it exactly upward. These are what our shift transformation looks like. Now, when we're talking about stretches and compressions, you want to think of it like a rubber band, how you're stretching it vertically. If you get a rubber band and you stretch it vertically, it gets wider. So if I do a vertical stretch of my function x squared, it might look something like this. The blue one is your transformed function. The red one is your parent. Notice that if you imagine like a rubber band and I stretch it upwards, it gets skinnier. Now, I can also do a reflection across the x-axis or the y-axis. If I wanted to do a reflection across, let's say, the x-axis, I'd get this. It would flip upside down across that x-axis, kind of like a mirror in a sense. If I want to reflect it to the y-axis, well, it'll be the exact same graph. And the reasoning is because if I reflect it across the y-axis, it's this exact same shape. If I wanted to fold it, you would have the exact same image, just because it is symmetrical across the y-axis. So sometimes it might not matter in that case. However, now, when we're discussing transformation, we need to know how these transformations play a role algebraically. This is how it looks visually. Now we gotta mess with it algebraically. How do we know if a shift occurs? How do we know if a stretch occurs? How do we know if a compression or any of that matter actually occurs to our function? Well, let's take with shifts. When we shift our function, let's take any arbitrary function. I don't care what parent graph it is. Let's take f of x to be our function. Parent graph. If I take a function f of x to be my parent graph, we say that f of x minus, let's do h plus k will represent shift transformations. They will represent your shift transformation. In particular, your k is going to be your vertical transformation, vertical shift. The minus h will represent your horizontal shift. That's how they will play a role for our function in particular. So this means you need to understand what it means to have a function, inputs and outputs. If I have an operation, an addition or subtraction operation inside my function, I will have a horizontal shift. If it is outside my function, it'll be a vertical shift. So let's take 3 examples. Example 1. Let's take f of x equals, let's take my parent graph to be equal x squared. Now, if I ask you transformations for f of x equals x minus 3, so I've written this differently. However, this is the form I want because, in particular, our function takes our input and squares it. So if I have my input being subtracted by 3, or adding by 3, this is still my parent function because the entire thing is being squared. This is inside my function. This is inside function, which is a part of our input. Now, if I do something like minus 4, this piece is outside my function. Why is it outside my function? Or outside my parent? So that's better. It's a better way to phrase it. It's outside my parent function. Because x squared, the thing that's being squared, is over here. And this is clearly outside of that. So that's why I say it's outside my function. And now if we go back to our definition over here, The k is outside my function, so it's going to be a vertical shift. The h is my horizontal transformation, so it's going to be inside my function, which is going to be a horizontal shift. So because this is negative 4, we have to take the negative type of vertical transformation, which this is going to represent down 4, or it's going to shift downwards 4 vertically. Now, the problem about inputs is that when you look on your graph in your parent function, let's say we take a graph here. If I look it over here and I did -3, -5. The blue one is our transform function. The red one is our parent. Notice that I move right 5, but right 5 should be positive. So why is it moving to the right 5 when I have -5? That's strange. If we look over here, my formula included -h. That means I will go in the opposite direction as your shift is supposed to go. So normally, intuitively, you might think, hey, if it's a +3, I'm gonna go right 3. However, because our function states that we're going -h, we have to go to the left 3. Left 3. This is a horizontal transformation, so we're either left or right. But in this case, we're going left 3. And I encourage you to think about this in terms of function. It makes sense for outputs, but for inputs, understand that those values that you're subtracting by 5 happens before your actual image appears. And because it happens before your image appears, your image will actually look like it's going to the right instead of to the left, because the transformation already happened for the input. That is why we're going to put -h. If I had done +3, we're going to go to the left 3. If I had done -3, we're going to the right 3. And it is because in our inputs, our operation will always be inverted. Instead of positive, it goes negative direction. Instead of maybe a shrink, it goes into your stretches. This is going to be a key theme that we're going to learn. And everything in our horizontal transformation will always have an inverted effect. And I use the word inverted similar to the word inverse, if you guys remember what inverse means of an operation. So, going back to our little over here, we have our function is going to move to the left 3 and down 4 of our parent graph. So let's just check that on here real quick. Let's write that down. So if I had x +3 squared, and then I subtracted 4, you'll notice that it is the exact same graph right here. Why does it look bigger, actually? Let me see. Let's see. No, it just looks bigger, but it's not. It's not actually bigger at all. It's just because of the scope of it. But it's the exact same size. However, our graph, this vertex, we're going to move it to the left 3. Boom, boom, boom. These values on the grids are by half numbers. And then we're going to go down 4. Boom. And there's where our vertex is located. Vertex is the middle of your graph or your parabola. So boom. And you notice the point is located at -3, -4. So now let's go back over here. Let's give another example. That's example 1. Let's do example 2. Let's let g of x, I'm using different letters for functions so we don't get confused. Let's let g of x equals, I don't know, square root x be our parent function. Parent graph. If this is our parent graph, we gotta know what our function is doing. It's taking your inputs and square rooting it. In particular, it's getting the positive square root, not the negative, just the positive square root. So now, let's suppose that I should call this actually, let's call this f of 1, just to name it. Let's call our new function g of 1 of x equals x minus 4 plus 1. All right. What transformations do we have? This is our transform function. How is it moving from our parent graph? Well, I have this minus 4 is inside the square root. The square root is our function. Remember that. It is our function. Technically speaking, you don't see it, but there's a parentheses here all under the square root. There is a parentheses. So if we treat it like how we did over here in this little example, whatever our function is, if it's inside my inputs, which is inside my function, my parent function, the square root, then this will be a horizontal transformation. And in particular, because it's a horizontal transformation, we got to do the inverse direction. So it's going to move right 4. This one, however, is outside the square root, which is the parent graph, which means it's a vertical transformation. And because it's a vertical shift, vertical shift, we're going to go up 1. It is exactly the direction that is intuitive with the signs. If it's positive, it goes up. If it's negative, it goes down. Intuitively, that's how we operate. So, that's example number 2. We're able to deal with the square root function. All right, and then if we want to look at it in our graphs, let's just look at that behavior. Let's now look at square root of x. This is what square root of x looks like. So if you didn't know what it looks like, now you have an idea. This is also important for your parent graphs. Now, if I did the transformation function, square root x minus 4, you notice that moved to the right. It moved this little base over here all the way to the right 4, that starting point. Then, so it does move in the opposite direction. Then we also added a 1. Well, now it moved up 1. This looks like 2, but it's not, because each margin represents 1/2. So it is 1 unit. You know, this is exact. And then every single individual point on this graph will have that same shift. All I'm doing is imagine me copying and pasting this graph and then just moving it right and up. I didn't stretch it. I didn't change the way it looks or anything. No, I just moved it. Now, we got the last example. Example number 3. Let's take h of x to be our parent function. And this time, h of x is equal to x, 1 over x. This is the reciprocal function. Well, let's take this to be the parent. And then instead now, we're going to work with h. I'm put a sub of 1 to represent, the subscript 1 to represent the other function that's being transformed. Let's let this be 1 over x plus 2 minus 6. Well, we got to know what our reciprocal function is doing to our x in particular. Our reciprocal function is doing 1 divided by our input. 1 divided by our input. That's the operation of our parent function. So, 1 divided by our input. However, this right here, x plus 2, you don't see it, but that is inside of our parent function because we're doing 1 divided by our inputs. And in this case, 1 divided by x plus 2. So this 2 is part of our horizontal shift. The reason why I want to introduce functions as these type of machines with inputs and outputs is so when we work with transformation, it doesn't matter what function we're working with, what parent graph, we're able to work with it. I had a lot of issues with students who've worked with transformation before, but they struggle when they see a new type of function. And I tell them all the time, it's the same rules that apply, you're just using a different type of graph. Just because you haven't seen what the exponential function does, you should still be able to know how to work with its transformation. And this minus 6, it is outside of our parent function. Our parent function is doing 1 divided by whatever. This is clearly outside of that. So this is our vertical shift. In particular, this right here means down 6. In particular, this means to the left 6. Remember, if it's inside my function, my parent function, it has to be inverted direction. The direction is inverted. So this is left 2. down 6 and left 2 are our transformation for our transformed function. And then let's see how that looks on the graph. So now let me change it up. I'm going to have f of x equals 1 divided by x. Remember, this is your reciprocal function. It has this asymptotic behavior. Boom, boom. Now the new function, 1 divided by x, what is it, plus 2. Well, do you notice that it moved this piece right here? So I like to look at this pointer here, 1 comma 1. Because that's a easy point to just look at for your reciprocal function. 1 divided by 1 is 1. So if I put my input with my and get an output, it'll be 1. If I move that, let's see, the starting point's over here. And if I move that 2 to the left, 1, 2, this is where it's located at. Negative 1. It's very hard for the Desmos to actually calculate or to get the exact value. But yes, negative 1 comma 1. Boom. I like to use that as a reference point. Then we're also going to subtract 6, which means 6 down. Well, now if I zoom out, you can see that from that point over here, I move 6 down. So now it's over here. So this is the idea of transforming different types of functions. And this is how mathematicians graph functions without a calculator. Calculators will use points and then calculate each individual point. It'll calculate each individual input and calculate its output using a table. However, that is very tedious for mathematicians. So what we do instead is see if we can find the transformation in an easy manner. If we're able to do that, then we're good to go. So boom, we can just write f of x to keep it consistent. And I should write h of x, but this is Desmos. I don't really care too much about it. But our transform function is down 6, left 2. Those are our 3 examples. I wanted to use a quadratic, I wanted to use a square root, and I wanted to use a reciprocal function. So now we're going to talk about stretches and compression. And we're not fully done with shiftings, but we'll talk about that in a bit. I've covered the main parts. It will play a role later on, but not right now. So stretches and compression. Let's let f of x be the parent function. The author of the book, Stewart, states that, hey, if I have a number times my function, if this guy is, or if your number multiplying the outside of your function, this will be counted as a vertical transformation. Now, we got to decide, is it a, oops, spelled vertical wrong. We got to decide, is it a stretch or is it a compression? We say it's a vertical stretch if that value is bigger than 1. If it's equal to 1, there is no transformation at all. There is no stretch at all. If it's bigger than 1, it's a vertical stretch in our case. And if it's bigger than 1, we're going to say, we say f has, I'm going to say up sub 1, f1 has a vertical stretch of factor c. We say it has a vertical stretch of factor c. It is being vertically stretched by a factor of that c, if that c is bigger than 1. However, if we have c times f of x, let's call it f2, where c is smaller than 1, instead we will have a vertical stretch, or not stretch, I'm sorry. We will have a vertical compression if c is in between 1 and 0. And I'm just going to put the absolute value. And the reason why I put the absolute, I should put absolute value here too. Well, it doesn't really matter with the first one, but I put an absolute value if your c is in between 0 and 1, i.e. it's a fraction smaller than 1. If it's a fraction smaller than 1, then we say f has a vertical compression of factor 1 over c. Or I'm sorry, a factor c. But that c will be a fraction, of course. It'll be a fraction. So We have a vertical stretch and a vertical compression if you have a number multiplying outside your function. It's a stretch if that number is bigger than 1. It's a compression if it's in between 0 and 1. And I put the absolute values. The reason why I put that is because negative numbers, negative does not play a role in stretch / compression. It has nothing to do, the negatives have nothing to do with stretches and compression. So, what do I mean by that? Well, let's take an example. Let's let our f of x be our function, x cubed. This is the parent graph. Parent. If I were to take, let's say f of 1 of x, let's take this as 3 times x cubed. Well, our parent graph, our parent function, is cubing our inputs. Clearly, the 3 is not being cubed. The 3 is not being cubed. So technically speaking, the only thing being cubed is the x, which means 3 is outside of our function. 3 is bigger than 1. So we say this is a vertical stretch of factor. It's a stretch because 3 is bigger than 1. It's a vertical stretch, or it's a vertical transformation because it's outside of our function. It's a factor of 3. Now, let's take another one. Let's instead take f of 2 of x equals 1/3. Oops. 1/3 x cubed. Well, the thing that here is that it's going to be a vertical stretch of, oh, I'm sorry, not stretch. It's less than 1, so it's going to be a vertical compression. It's going to be a vertical compression of 1/3. So we're still keeping that factor. The factor is still whatever we're multiplying by. However, it's a compression if it's less than 1. If it's a fraction less in between 0 and 1. It's a stretch if it's bigger than 1. And let's bring out why I say negatives don't really play a role. If I had a third one, let's say this is negative 4x cubed, we are still going to say this is a vertical stretch of factor 4. We will still say it's a vertical stretch because 4 is bigger than 1. We don't really care about the negatives. Don't even look at the negatives for vertical stretch and vertical compressions. It's still a vertical stretch because 1 is bigger than 4, or 4 is bigger than 1, and it's a factor of 4. So what does this mean graphically? Let's go to our graphing calculator. So I have all this stuff up already. Let's take x raised to third power. Actually, it might be easier if I do x squared. It'll be easier if I do x squared. All right, let's do a vertical stretch of a factor of 3. 3x squared. Well, it's a vertical stretch. What does that mean? Imagine a rubber band, and I grab the top ends and the bottom ends, and I stretch that rubber band. If I stretch it up and down, that rubber band will get skinnier. So my parent graph is the red one in this case. Parent graph is the red one, and my purple one is going to be the transformed one. It got skinnier. It got stretched vertically. So if I look at this, let's look at the point on this function 1, 1. That same input 1, 1, that same input 1 will now have an output. Instead of being 1, it'll have an output of, where is it located at? 3. I multiplied that output by 3, which makes sense because 3 is multiplying outside my function. So that is the idea. Instead of 1, 1, I move to 1, 3. And if I do that for every single point here where I multiply the output, it's going to get skinnier. It's going to be vertically stretched. Now, what if I took it as 1/3? We know if it's 1/3, it's smaller than 1. So it should be a vertical compression of 1/3. Well, take that rubber band now, Imagine if I grabbed the top ends and the bottoms and I squished it together. Your rubber band is going to get wider, which is exactly what happens here. Now, when it gets wider, let's look at that input 1. Where do you think that output's going to be? It should be 1/3. Well, let's look over here. This is going to be 0.333. Now, you should have a bar over it, but unfortunately, calculators don't do that. But this is exactly 1/3. And this is why it gets wider. So, that's the idea of vertical transformation. Let's go back over here now. Or let's actually just show what happens if I throw a negative on there. Let's suppose I did a negative. Oh, it flipped it upside down. However, I guarantee you, there is no difference. If I look at that point, 1, 1, it's going to be at negative, it's going to be at 1, negative 0.33. So it still has a factor of 1/3. It's just now negative. Don't put the negative on there. That does not play a role. It plays a role in reflections, which we will talk in a bit. So, I just want you guys to be aware the negative does not play a role in stretching and compressions. So that's the vertical stretch / compressions. Well, now that I've talked about that, we have to talk about horizontal stretches and horizontal transformation. So let's take f of x to be my parent graph again. Parent. I'm going to use a different letter this time. I know Stuart used the letter C, but I think that's confusing using the same exact letters. So I'm going to use the letter B. So f of b of x, right here. F of b of x, this right here will represent a horizontal if your value is multiplying inside your function. If it's multiplying inside your function, then it's going to be a horizontal compression of, or it's going to be a horizontal compression if b is bigger than 1. Some people call it compression, some people call it shrink. They mean the same thing, shrink compressions. Now, it's a horizontal compression if b is bigger than 1. But wait, over here, I stated that if your c was bigger than 1, it's a vertical stretch. It's a stretch. Over here, I said now that if it's bigger than 1, it's a compression. Well, this plays the same idea as our shifts. If it's inside my function, it will have the inverse operation. Instead of it being, if it's plus 3, instead of it going to the right 3, we're actually going left 3. It's the opposite. It's the inverse direction. So in this case, instead, it's still a horizontal transformation because it's inside of our function, but now instead of being a stretch, it becomes a compression instead. It's the inverse. Instead of stretching, we're compressing. So b is going to be bigger than 1 if b is bigger than 1, we have a horizontal compression. And then we say f has a horizontal compression of 1 over c, or 1 over b, I'm sorry. Now this has some things we got to talk about. Oops, why is it not popping up? I'm not sharing anymore. Share application window. This has some things that we need to discuss because there's a lot of things that are not said. Why is it not sharing? Oh, my internet went out, unfortunately. So I'll edit this, that way you guys can see it and everything so you guys don't run into this issue. So this has a horizontal compression. I'm going to get my charger while I'm at it too. That way I don't come into any issues at all. To reiterate, this has a horizontal compression of 1 over b. Wait a minute, that sounds funny. Well, that's also inverted, that's why. Because it's inside of our function, we have to inverse things. So, let's take an example of that. Example. What if instead I had f of, let's do x squared, my parent function. This is the parent. Eventually, you guys will get used to not me calling it a parent graph, but right now I'm just showing you what each of the parent functions are. Let's take f of 1 of x equals, let's take it to be something like 2x squared. Well, this right here is inside, this is also being squared. And because it's being squared, it is inside my function. My function is squaring. So, because it's inside my function, this is going to be a horizontal. Now, this value is bigger than 1. I stated if it's bigger than 1, it's not a stretch if it's inside my function. It's instead a horizontal compression. Remember, we always got to go to the inverse direction, or in this case, the inverse operation or inverse action. It's a horizontal compression. So in a horizontal compression, we can say it has a factor of, it's a horizontal compression of factor. Now, if I look earlier, it says, we say that it's a horizontal compression of 1 over b if it was b times x, which means we reciprocated. We have to reciprocate our factor for any horizontal stretch / compression. So instead of 2, we say has a horizontal compression of factor 1/2. And that's very important. Now, if we look on our graph, however, it's going to look a bit weird. If we look on our function, let's do 2x squared. Let's take our input 1 again. I like that input a lot. 1, 1 right here. Now, with that same value, that same input 1, where does it touch the purple graph? It touches it all the way at 4. Wait, how did they get 4 as an output? Well, notice that 2 has to be squared too. This is a single term. That means we apply the exponents to both of these guys, both factors. So it's 2 squared, which is 4, times x squared. And that is why we get 1, 4. Whoops, all the way over here. All right? So a horizontal compression or stretch may seem stronger at times just because than a vertical stretch / compression, because the function itself is applying its transformation on it. Whereas if it was outside my function, I don't get to apply my function to it. So this has a horizontal compression of a factor of 1/2. Great. Well, what happens now if, let's say we have that parent function. What happens instead if I have f of b times x, and let's let b be less than 1, bigger than 0. I'm only saying that because I only care about it being positive. The negatives don't matter. It does not matter at all. I'll put an absolute value just so we're clear. It does not matter at all. All right. What if b was not bigger than 1? What if it was less than 1? Less than 1 positive, of course. Then we say this is a horizontal. Well, earlier I said it would be a vertical compression, but now because it's inside my function, I say it's a horizontal stretch. We say it's a horizontal stretch. And we say it is a horizontal stretch factor 1 over b as well. Same rule applies. However, this is going to look a bit tricky because, let's give an example. Let's take the function f of x equals x cubed again. Let's look at that function right here. This is our parent. Actually, yeah. Actually, let me use a different one. I'll use a non-power one just to give you guys better illustration. Let's say 1 over x. Yeah, 1 over x. Let's take 1 over x. Well, 1 over x, and then this is the parent. Now let's take the transform one being 1 over 2/3 x. 2/3 x. Now, this is inside my function. Remember, my reciprocal function is doing 1 divided by whatever my input is. So this is now 1 divided by, well, if it's whatever my input is, well, now this is inside my function. It's being reciprocated. So now this guy is clearly a horizontal compression slash stretch. I don't know which one it is, but I know it's a horizontal whatever. Now, 2/3 is less than 1. So if it was a vertical transformation, we would say it's a vertical compression. However, because it's inside of our function, we have to do the opposite or the inverse. So now it's a horizontal stretch. And we say a factor. Now, we can't say factor of 2/3. Remember, when we're dealing with this, we always do the inverse operation. Instead of saying factor of 2/3 like we did with the vertical transformation, we have to reciprocate it. We have to reciprocate it. So it's a factor of, oops, I said of twice. It's a factor of 3/2. You always have to reciprocate that guy. Always have to reciprocate it. So I'll write that down. Always, make a little star. Always reciprocate factors for horizontal stretch slash compression slash shrink, whatever you want to call it. But yep, we have to reciprocate. If we look over here, we had 2 times x, but because it was a horizontal compression, we have to reciprocate 2 to 1/2. Same over here. Now it's 2/3. It's still a horizontal transformation, but it's a horizontal stretch this time. And we have to reciprocate 2/3 to 3/2. It doesn't matter if it was negative 2/3. If it was negative 2/3, you're still going to have a horizontal stretch of factor 3/2. We're not going to apply the -2 at all. The negative does not matter. So now we can take some examples of all this stuff. So let's take another example. Let's do square root x. Or I'm not even going to tell you the parent function anymore. You can figure out what the parent function is. Let's take 3/4 x in this case. What is this transformation from the parent graph square root of x? Well, this is inside the square root. So immediately this has to be a horizontal. Now we got to decide if it's a stretch or compression. It's less than 1. So instead of being a compression, because it's inside of our function, it's a horizontal stretch of 4/3. We got to reciprocate it. We got to reciprocate it. Now, if you want to look at the graph, you can take a look at the graph. If we look over here, let's do square root of x just to be sure. Square root x, boom. And then if I want to do the horizontal compression, square root 4 divided by 3 of x, boom. Oh, not 4 divided by 3, sorry, 3/4. Boom, we have that. Let's take the point square root of x. Let's do 1, 1, which is over here. Well, 1, 1 is now going to be moved to 0.866, around there. And that's because we're doing the square root of 3 divided by the square root of 4 as well. So that's square root of 3 over 2. And that's the reason why our output for 1 looks very strange. All right, so that's the idea of horizontal compression, horizontal stretch. However, there's a small little concern that we have to talk about. I'm not going to close that off. Small little concern. This is only going to apply for horizontal stretch horizontal stretch or compression. Let's take a function. Let's take use this. Let's take f of 1 of x equals 2x minus 3 squared. Let's take that guy. So the parent graph, well, I don't want to use 3. 3 is too rough. Let's do 4. The parent graph, oops, no, I'm not going to do that. It's confusing. The parent graph of this guy is a quadratic. Parent is x squared. The parent is x squared. What this means is, hey, we're supposed to move that right 4 and horizontal compress a factor 1/2. We're supposed to, but that's not really what we're supposed to do, because Normally, this is correct. We don't have to worry about that. It is a horizontal compression of factor of 1/2. However, this is incorrect. It is not moving right 4. And let's just check that just to be sure. It should not be that. Let's do square or x squared. X. And now let's do the new one. Let's do g of x equals, and let's do 2x minus 4. You would think it goes right 4. You would think. Let's look at this vertex. This vertex is at 0, 0. And if I move right 4, I should be over here. I should be located over here. But it's located at 2. I didn't move right 4. I moved right 2. But why? It says minus 4. Turns out, when you're doing these horizontal compression / stretching, you have to be very careful. This is actually, you have to factor out your horizontal compression with every term inside. What do I mean by that? Well, this is exactly what I mean. You have to do 2, factor out a 2 from both terms. If I factor a 2 from this is x. Factor a 2 from that is minus 2 squared. This is actually what your equation is supposed to look like. However, of course, we don't write it that way. But when you're doing transformation, this is what's being happened. It's whatever is multiplying the entire term inside your function. So this is the reason why we move right 2 instead of right 4. This is only going to happen with horizontal compression and horizontal stretch. So be very careful with that. Be very careful with that. So let's take another example just to be sure. Let's say I have f of 2x equals, and then I did square root of 3x plus 4. This means right here we're going to have a horizontal compression of 1/3. Factor of 1/3. However, now because we have to actually factor it out, this actually becomes 3 times x plus 4/3. So we're actually moving to the left 4/3 units. So be very, very careful with that. Very, very careful. And the last thing we got to talk about is reflections. So, the last thing is reflections. The main thing we're going to be looking at is reflections from about the y, about x-axis and y-axis. Reflection about the x-axis and the y-axis. In particular, that's where the negative plays a role. So, if I have negative f of x, right here, where f of x is the parent graph, or let me see, the parent graph is f of x. Let's call this the parent. If I call this the parent, then negative f of x is going to be a reflection, reflection about the x-axis. It's a reflection about the x-axis. Now, if I have f of x and the negative is inside my function, this is a reflection about y-axis. So, you might have to reflect it through the x-axis or the y-axis. Think of it like a mirror in a sense. So, let's give an example. Let's say f of x equals x squared. Well, this is the parent. Well, how does that change from f of x equals negative x squared? Well, the negative is not being squared. So this is outside my function. So this is a reflection about x axis. This is a reflection about the x-axis. So if I actually look at my calculator and I threw that in, x, those are negative, boom, it's going to flip it upside down. That is the reflection across the x-axis. It moves every point in that direction. So that's great. That's the reflection about the x-axis. Now, what if I wanted to do a reflection across the y-axis? Well, that's inside my function. It has to also be squared. But I don't get another function. That's weird. I only have one. Where's my parent graph? My parent graph is still here, but they're the same functions. Because a negative times a negative is a positive. Well, if you think of it that way, you're reflecting across the y-axis. If you notice, if you flip this, if this was the mirror itself that you had to flip, you'd get the exact same image. This is fully symmetrical on the y-axis. So when you reflect it, it is the exact same graph. You only see the reflection on the x-axis. So that is the idea of reflections. You can have it on the x or you can have it on the y. Well, let's do one last example now with that. Let's do f of x equals negative x square root of x. Where your parent graph is square root of x. And then let's do 2, and let's do f of 3 equals square root negative x. Well, this is outside my function, so it should be reflection about x. Reflection about x. And this is inside, so it should be a reflection about y. So if I do that, square root of x. Oops, what does this have that exponent? Oh, good. If I do it on here, it'll be a reflection, so it'll go downwards. It's a reflection about the x-axis, so it goes downwards. And do you see it creates that parabola sideways? But if I throw it inside here, it's going to go to the other side, reflection about the y-axis. Now, you can't have a square root of a negative number, so you can only have negative inputs because a negative of a negative is a positive. You can square root a positive value, so you have to have a negative number because it's multiplying by a negative to get a positive value. You can't have it anything on this side because you can't square root a negative. So that's the idea with reflections. That's the main gist. So we talked about all of our main components. Now let's combine all of it together. Shifting, compression, stretches, and reflections. Let's combine all of it together. So we can say that we have C times F, if we have a negative or not. Let's combine most of it together, not all of it. X minus H plus K. This is what I would use to help me remember things. All right, if you have a function, and this is more particular, this is supposed to be H divided by B. Sorry about that. This will tell me how I'm transforming. This is going to represent everything outside of your functions. Let me just write that down. Outside function is a vertical transformation. So that can include, going up, down. It could also include stretching upward, stretching vertically stretching, vertically compressing, and it can also include reflecting across the x-axis. Why? Well, let's take a graph. If I have a point and I reflect it across the x-axis, what kind of transformation did I just make between these? This is a vertical. If I reflect across the x-axis, it will be a vertical transformation. That's why every operation happening outside my function will be a vertical transformation. Everything inside my function, is a horizontal transformation. It's a horizontal transformation. Always, when you do your horizontal transformation, be careful. These are the tricky ones. Do inverse do inverse operation. And be sure to factor b. You always got to factor b just in case. So in this case right here, over here, our horizontal transformation is also reflecting across the y-axis, because if I take 2 points right here and I reflect this point across, if I take this point and reflect across the y-axis, this right here, this transformation has to be a horizontal transformation. So everything inside of our function will be a horizontal, inside our parent function, so I say parent. Inside our parent function will be a horizontal transformation. That's why it's a reflection across the y-axis. Now, let's suppose I had some crazy function, example now, f of x equals, let's say, 3 over x minus 4 plus 2. This is where it can get slightly difficult. Because, whoops, let me erase this. We're combining multiple things together. If I throw a negative here, doesn't really matter. Now, this 3, technically speaking, you have to visualize this a bit differently. Technically speaking, this is negative 3 times 1 over x minus 4 plus 2. This is why I say you got to visualize things a bit differently. You got to know how these operations are actually working. So with this in mind, this 3 will represent a, and it's negative, this is a reflection about x axis. This right here is a vertical stretch. It's not a compression. It's a stretch. Even though you had negative on there, it is still bigger than 1. It's a vertical stretch of factor 3. This right here will represent, so factor of factor 3. This will represent, wait, it's minus 4, but it's inside of our function, so we have to go in the opposite direction. So we have to say right 4, a vertical shift to the right 4, and this right here is outside of our function, so we have to say up 2. That's example 1 of combining all of it together. Well, now let's go to example 2. Let's take f of x equals, let's do absolute value. I don't want to do absolute value. Let's just do cubic. Let's do x negative x what is a different color? I don't like that color. Let's do 3x plus 9 squared minus 4. In this case, your parent graph is reciprocal. Let's say we take the parent graph being the quadratic. Parent is y equals x squared. Let's take this to be our parent graph. Well, then the transformation happening on our parent graph, well, all of this is inside my function. So the problem that I see, this is clearly down 4. It's outside my function. I can deal with that easily. However, there's a 3 here. The moment you see that, you have to factor it out. You have to factor it out. So this actually becomes 3 parentheses, make a big one, x plus 3 squared minus 4, which means this is down 4, which we already stated. That doesn't change at all because it's outside my function. But inside my function is left 3. We say left because we have to go in the opposite direction. And this right here is a horizontal. All of these are horizontal transformation inside. But we have to do the inverse. So instead of a horizontal stretch, we say it's a horizontal compression. And we always have to reciprocate our horizontal compression or stretches factor. If I reciprocate 3, we're going to say 1/3. So you got to be very careful with that. Always reciprocate your horizontal stretches and compressions. Everything inside has to be a horizontal transformation. Everything outside my function is a vertical transformation. We'll talk more about how to graph these later, but this is the gist of all these transformations. I want you especially to highlight these important pieces right here. Let me put a star here. And then the last star will be reciprocate. Reciprocate, horizontal, stretch, / compression. If it's a horizontal stretch / compression, your factor is always going to be reciprocated. You have to flip it. All right, so that covers that, and I will catch you guys later. Take care.